Everyone, we are back, and we are now going to get into our problem set 5 solutions. So hopefully you're busy studying for the exam and everything is going well. So let's go ahead and get started. I'm actually going to see if I could hide this. There we go. Perfect. So let's look at the phase diagram below. So again, I'm probably going to have to do some eutectics and peritectics and all of those other good, all that good stuff. So just to remind ourselves, eutectic, we go from a liquid to two-phase solid region. Eutect, I'm going to just do the same thing. Oid is the same thing, but one solid region to a two-phase solid region. Peritectic, we go a liquid plus alpha to a single-phase solid region. A new phase solid region, these are all invariant points. The degrees of freedom should be 0. And then an oid will be a gamma plus alpha to a beta. So, let's label all the invariant points. Let's do all the congruent melting points. So here is one congruent melting point. So for the congruent melting points, I'm going to go and do a square. So I've got a square here. I've got a congruent melting point here. I've got a congruent melting point right here. I've got a congruent melting point right here. I have a little bit of a congruent melting point right here. I have kind of one here as well that I can kind of melt through. So anyways, those are my congruent melting points. So I'm actually going to erase so you can kind of see what else is happening. And so let's also actually label the phases too. So our phases here, this will be this plus liquid, and then it's going to be, this is going to be this two-phase region, 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 and you can kind of see, and we can see, and we can see added here. This is an alpha, and it transforms to beta, so this is beta plus liquid here, and this is going to be this plus liquid. Actually, add that plus liquid here. This right here is going to be this phase plus our liquid right here. This is going to be right here, or this phase also plus liquid. This phase is going to be this phase plus liquid, and this is going to be liquid plus this phase. This is going to be liquid plus this phase as well. This is going to be liquid right here plus this phase. This is also going to be liquid plus this phase. This is going to be right here, this plus liquid, and this is going to be this phase plus our alpha phase right here. So that's what we've got. So again, I'm going to erase. Those are all our kind of two-phase regions, but again, those aren't too important. Now, for eutectic, I'm going to do this triangle, let's do circle, and let's do another square. So I need the invariant points. So immediately I see this is going to be eutectic because it goes from liquid to a two-phase solid region. This is going to be my peritectic right here. And let's see, what else do we have here? This may be, there's usually like a little tiny, so you may actually put a eutectic right here as well. This is definitely a eutectic right there. Again, this may be a little eutectic right there. And this is also eutectic here. And anything else? Nope, that's pretty much it. So let's see what else we have in store. So label the phases. Again, we kind of did that quickly, but you would know kind of the rules, and you're experts at that at this point. I need the degrees of freedom. So I am doing a multi-component phase diagram where temperature and pressure, so D degrees of freedom equals components minus the phases plus 1. For a single component phase diagram, we have C plus P, actually C minus P plus 2. But we're not going to use that for most of our problems, So let's do the degrees of freedom at 30% calcium, 50% and 500 C. So I'm at 500 C, I'm 30% calcium, so I'm right here. So how many phases I am in? I'm in this two-phase solid region. So my components are always 2, because what am I mixing? I am mixing Ag, silver, and calcium, minus 2 plus 1. So I have 1 degree of freedom here. Does that make sense? If I change temperature, so if I try to go up in temperature, if I try to go down in temperature, my composition, I'll basically move out into these two phase separated regions. So if I change temperature, my x-axis, my composition is fixed. If I also change, essentially my composition here, so if I change composition, let's say I'm right, let's say my initial composition is, here, now my temperature is fixed. So I have 1 degree of freedom, the other is fixed. So that makes sense. What about at 80 atomic percent calcium? What about at, okay, so same problem at 900 C. So 30%, 900, I'm in a single phase. So my P is 1 now. So C minus 1 plus 1. Components is 2, so my degrees of freedom is 2. Why is that? Because I could change over here, I could change composition, I could change temperature independently. I have 2 degrees of freedom there. And what about at 900 C and 80% calcium? So 80% calcium, and then we could even go to 500 here. So again, still 2, because you're only in a single phase. What's the maximum solubility of Ag and Ca and Ag? Very, 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 very small. So basically almost 0, effectively. So pretty insoluble. So pretty close to 0. I have a sample at 40 atomic percent calcium. Actually, let's change our color here. I want to change. Let's go to a different color. I want to go with the red. All right. So I am at 40 atomic percent calcium. Let's see what we had here. 40 atomic and 400 C. What is the concentration and fraction for all these things? Okay, excellent. So 40, 400, so I'm right here. So I can see that I am going to have, and actually I'm going to kind of delete this here. So I'm in a 2-phase region. So I'm going to have a concentration of Ag2Ca. That concentration, even though I'm at initially at 40%, is going to be this 31, 2, 3. So basically around 33% atomic percent Ca. My concentration of, let me erase here a little bit, AgCa is going to be 50. Now, the fraction that's in this Ag2Ca, if I'm right here, again, I go to the opposite. So I take this difference here over my tie line. So always 50 minus 33, and then now this will be 50 minus 40. What's the fraction in my AgCa? It's going to be the same thing, 50 minus 30, but now, again, if I want this, I go on this direction here. So kind of makes sense. I should be a little bit more, I'm a little bit closer to A2Ca, so that is going to be 40 minus 33. And that's it. Fantastic. Now it says draw the free energy curves at a temperature of 800 C for AgCa. So 800 C looks like this. So if I were to draw my free energy curves here, so for example, let's just kind of try to match this up. Here. This is my Gibbs free energy. So you see here, I'm in a pure, basically single phase region. Actually, I kind of basically almost start out with this 2-phase region. So let's just kind of put this here, and then let's put another mark right here to indicate where we're in this 2-phase region of the liquidus. And then let's also put a mark right here and right here. So I'm going to say that this, basically Ag is this curve, this color. This phase, I should have made the other color. This phase right here, liquid, I'm going to change this right now. This blue is my liquid, and then finally, I'm going to change here. That orange is my beta here. So I am initially a solid, but I'm basically immediately in that 2-phase region. So I've got a, basically a free energy curve that looks like this. And I also, from here to here, I have a common tangent with my liquid. So there's a common tangent that looks, there should be a little bit even easier interface like this, from here to here. So I've got that common tangent curve that looks like this, like so. So in between here and here, I am a 2-phase region. Now, I'm a single-phase region for a while. So let's go back to here, let's change it to my color, and then I am just kind of hanging out, and then eventually I'm at 2-phase region here, and then I'm going to get to my orange. So my orange kind of comes in out of nowhere, and then I have, again, one more common tangent as such. So there we go. I guess you could kind of basically play around and add these. That's cool. Again, new time playing with this. So those are my free energy curves. So I have common tangents when I'm in a two-phase region because why? I know that my chemical equilibrium are equal to one another. So in a liquid phase and a solid phase. Fantastic. Let's look at another phase diagram. So let's go ahead. We kind of know the system. So where are my congruent melting points? I always have one on the side, one on the side. Here's another congruent, here's another congruent, here's another congruent. There we go. So those are congruent melting points. Let's go ahead and label the phases. So again, liquid plus this solid plus this solid plus this liquid plus this same solid again, this liquid plus this solid, this, you know, you could get the picture. Liquid here plus this solid, liquid here plus this solid, because again, the two phases are touching. This plus this, this plus this, this plus this, and each of these kind of two-phase regions here. This is HCP. It already actually gives it to you here. So we got those invariant points, or excuse me, the phase diagram. And then let's kind of continue. Oops, my pen is, there we go. So this is a eutectic point, this is a eutectic point, this is eutectic, this is also a eutectic point. Are there any other invariant points? Not that I can see. So that's pretty much all it is there. So label the regions. What's the maximum solubility of Ag and ER? So how much Ag can I put in ER? Basically, this is pretty close to 0. How much ER and Ag? Well, this is a little bit better. So probably close to like ER and Ag, probably about 0. Not quite 0.05, like 0.25. I think so. I think that's pretty close. All right. What else do we have? So I have a simple at an x of ER equals 0.6. So right here, and a temperature of 1400 K. So 0.6, and I'm at basically this line here. So I'm right here. So what is the concentration of fraction? So we could draw our tie line again. So I'm at this initial composition. So I am in the liquid phase, and I'm also, so I have a concentration of liquid, concentration in the AgER phase. That is 0.5. The concentration in the liquid, this temperature, let's just call it 0.65. So my fraction of the liquid is going to be 0.65 divided by 0.5. Fraction in the AgER, again, my lever rule, 0.65 minus 0.5. So my liquid will be essentially a little bit opposite here. So this is going to be basically 0.6 minus 0.5. Yep, exactly. And then my fraction, the AgER, is going to be the opposite, so it's going to be 0.65 minus 0.5. That's it. Oh, excuse me, times 0.6. My mistake. 0.6. There it is. And then finally, draw the free energy curves for a temperature of 600 K for AgER. So 600, ooh, we've got some work cut out for us. So let's go ahead and let's erase everything else. So I need 600 K. So let's go ahead and let's try to draw this out, and let's pick out some. So I've got, I'm going to call this is going to be purple, this is going to be this color. Let's do another color. Actually, let's just start to kind of draw after this. So what would be a good way to kind of draw this? Actually, I'm going to draw the free energy curve like this right here. So I am in, up until this point up here, basically I am just my red curve, and then I have a common tangent from here to my purple line right here, and actually there's some infinitesimal basically region where I'm a two-phase region, but from here to here I have a common tangent, so between here and that point, and then I'm fully just single phase right here, and then actually I'm going to try to draw this out a little bit. So I have a common tangent, and then I also will have another common tangent right here with this curve that comes out of nowhere. And so we have another common tangent right here. And then let's add a new actually color right here. I'm going to do this color. So I'm going to have this material. I'm also going to have this material, HCP. So I continue this kind of procedure. So I have another common tangent here for this two-phase region. So this guy goes up and out of here. This guy, I have another common tangent right here. And then you see here, I have yet another common tangent between here and then all the way here. So we have another common tangent here. So again, that's how roughly you would sketch it out. The key idea is, again, the chemical potential is equal in all those different values. So that is it. So I hope this has been helpful. Review for the exam, do the practice exam, and you're going to do just fine. I look forward to seeing you on exam day, and the best of luck. All right, thanks. Bye.